Newton-Cotes methods approximate a definite integral by fitting simple shapes, straight lines or parabolas, over evenly spaced points, then summing the pieces. Two of the most widely used rules, the trapezoidal rule and Simpson's rule, both come from this same idea, just with a different shape per segment. Split the interval from A to B into n equal pieces. Each piece has the same width, h equal to b minus a divided by n. The nodes are x sub I equals a plus I times h for I running from 0 to n. Instead of integrating f exactly, replace it on each segment by something simple enough to integrate by hand, a straight line or a parabola, then add up all the segment areas. Start with the simplest possible case, just 2 points, A and B, one segment. Connect f of A and f of B with a straight line. The area under that line is exactly the area of a trapezoid. Average the two heights f of A and f of B and multiply by the width b minus a. That is the trapezoid area formula from geometry, nothing more. Now repeat this on every one of the n segments and add them all up. Watch the shared edges. Every interior node belongs to two trapezoids at once. Every interior node gets counted twice, once as the right edge of one trapezoid, once as the left edge of the next, so its coefficient becomes 1 instead of 1/2. Only the two endpoints keep the 1/2 weight. This is the composite trapezoidal rule. Endpoints weighted 1/2, every interior node weighted 1, all multiplied by h. Here it is in EES. Define f of x as a function of x, returning x squared. Build the node array and the function value array with a duplicate chain. The inner sum handles every interior node with weight 1. The two endpoints outside the sum get divided by 2 separately. To see the true convergence rate, we need a function that trapezoidal cannot integrate exactly at any n. Sign works well. Compute the trapezoidal estimate at several values of n and take the absolute error against the exact answer of 1. Doubling n, halving h cuts the error by a factor of 4. That is exactly what a slope of 2 on a log-log plot means. Error scales as h squared. Simpson's rule uses 3 points per panel instead of 2, the two ends and the midpoint, and fits a parabola through them instead of a straight line. A parabola hugs a curved function far more closely than any straight line can. Integrating that parabola exactly gives this formula. The classic 1/3 rule pattern, weight 1 4 1, scaled by h over 3. Because each panel eats two segments at once, one on each side of its midpoint. The segments have to pair up perfectly. That means n, the total number of segments, must be even. An odd number would leave one segment with no partner. Every odd indexed node, the midpoint of each panel, gets weight 4. Every even interior node, shared between two panels, gets weight 2. The two endpoints keep weight 1. Same setup as the trapezoidal code. Same function, same node array. Build the same node array as before. Then split the interior nodes into two groups by index parity. The even position group gets weight 4. The odd interior group gets weight 2. Simpson's rule is exact for any polynomial up to degree 3. X squared is degree 2, so the answer comes out exact to machine precision, 0 error. Same test function, same range of n. Watch how much faster the error collapses this time. Doubling n should cut the error by a factor of 16, not 4. A slope of 4 on the log-log plot is the signature of Simpson's rule. Doubling the number of points by 16 times the accuracy, versus only 4 times for trapezoidal. Newton-Cotes methods, week 3.